Imagine you hire a courier to deliver an important document across the city. The courier picks it up, navigates traffic, finds the right street, the right building, the right floor, and slides it under the wrong door, or delivers half of it, or delivers it twice, or delivers the pages in the wrong order. The courier did their job, they got to the right place, but the document didn't actually arrive the way it needed to. This is, surprisingly precisely, the gap that exists in computer networks between routing and delivery. And it's a gap that most people, even people who work with technology every day, have never thought about. Here's what routing actually does. When you send data across the internet, routing is the system responsible for finding a path from your device to the destination, moving your packets from network to network, router to router, hop by hop, until they reach the right place. It's a remarkable system, built on distributed decisions made by thousands of routers operating independently, and it works with extraordinary reliability. But notice what routing is responsible for: getting packets to the right network, not to the right application on the right device within that network, not in the right order, not without loss, not without duplication, not with any guarantee that what arrives matches what was sent. Routing is the postal system deciding which sorting facility your letter goes to, which truck carries it, which route that truck takes. It handles the navigation, but it says nothing about whether the envelope arrives sealed or torn, whether all the pages are inside, whether they're in the right order, whether the letter arrives at all, or whether you're even told if it doesn't. That set of questions, what happens to data after routing has done its job, is what delivery is about. Let's make this concrete with something you've almost certainly experienced. You're on a video call. Your connection gets a little unstable. What happens? The video freezes. The audio cuts out. Maybe it recovers, maybe it doesn't, but the experience degrades quickly and noticeably. Now you're downloading a file on the same unstable connection. What happens? The download slows down. Maybe it pauses briefly, but when it finishes, the file is complete and correct. You don't get a corrupted file. You don't get half a file. You get the whole thing, intact. Same bad connection, two completely different outcomes. Why? Because those two applications are using fundamentally different delivery models. The file download is using a delivery system that guarantees completeness. It will wait, retry, resend, do whatever it takes to ensure every byte arrives correctly. The video call is using a delivery system that prioritizes speed over completeness. It accepts that some data will be lost and moves on, because a perfect frame delivered a second late is worse than an imperfect frame delivered now. Neither of these is the right answer in general. Each is the right answer for its specific use case. And the existence of both, the ability to choose between different delivery models depending on what the application needs, is one of the foundational design choices of the internet. So what does delivery actually cover? What are the questions it answers that routing doesn't? The first is, did it arrive? Routing makes a best effort to move packets toward their destination. It does not guarantee that they get there. Packets can be dropped by congested routers, by faulty hardware, by links that briefly fail. The routing system doesn't know this happened. The sending device doesn't automatically know either. Delivery is about whether and how the system detects that data was lost and what it does about it. The second is, did all of it arrive? A file is not one packet, it's thousands, sometimes millions of packets. Each one travels independently through the network. Some might arrive, others might not. Delivery is about whether the receiving side gets everything, and whether the sending side knows if it didn't. The third is, did it arrive in order? Packets traveling across the internet don't always take the same path. Different packets from the same transmission might take different routes, arrive at different times, and show up out of sequence. The first chunk of a file might arrive after the third chunk. Delivery is about whether the system reassembles things in the correct order before handing them to the application. The fourth is, did it arrive exactly once? Under certain failure conditions, the same packet can be delivered more than once. The sender retransmits because it didn't receive confirmation, even though the original transmission actually arrived. Delivery is about whether applications have to deal with duplicates or whether the system handles it transparently. The fifth is, how long did it take? A packet that arrives is not the same as a packet that arrives in time. For a file download, timing barely matters, 5 seconds or 5 minutes. The file is the file. For a voice call, a packet that arrives 500 milliseconds late is useless. Delivery includes the timing dimension, the latency, the consistency of that latency, and what happens when timing requirements aren't met. Routing answers none of these questions. Delivery answers all of them, or at least makes explicit choices about which ones to answer and which ones to leave to the application. And those choices, what the delivery system promises and what it doesn't, are called delivery semantics. Different delivery systems make different promises. Some promise that everything sent will arrive, in order exactly once, no matter how long it takes or how much work is required to make it happen. Others promise only that they'll try, that packets will be sent, and whatever arrives with no guarantee of completeness, ordering, or acknowledgement. And there are systems in between, making partial guarantees tuned to specific use cases. The reason multiple models exist is that every guarantee has a cost. Promising that everything arrives means tracking what was sent, detecting what was lost, and retransmitting it, which takes time and processing. Promising ordered delivery means buffering packets that arrive early and waiting for the missing ones, which adds latency. Promising no duplicates means maintaining state about what's already been delivered, which consumes memory. For a file download, those costs are worth paying. You want the complete file. You're willing to wait. For a live video call, those costs are unacceptable. You cannot buffer a conversation while you wait for a lost packet to be retransmitted. The moment has passed. The gap is better filled with a glitch than with a pause. Speed and continuity matter more than completeness. Delivery semantics are about making that trade-off explicitly, deliberately, and appropriately for what the data actually needs. Here's why this matters beyond just understanding how the internet works. Every application you use makes choices about delivery, sometimes consciously, often not. A poorly chosen delivery model produces applications that are slow when they should be fast, or unreliable when they need to be consistent. Understanding delivery is understanding one of the foundational design decisions in any networked system. When an engineer decides which protocol to use for a new application, they're choosing a delivery model. When a game developer tunes their netcode to handle packet loss gracefully, they're working within delivery constraints. When a financial system ensures that a transaction is processed exactly once, never twice, never 0 times, they're solving a delivery problem. The internet doesn't deliver data the way a wire carries electricity, continuously, instantaneously, with no concept of completeness or ordering. It delivers data the way a postal system handles packages, in discrete pieces, with choices about tracking, confirmation, and what happens when something goes missing. Routing decides where those packages go. Delivery decides what it means for them to actually arrive.